Okay, so we're talking about 16.3 today, which is called the fundamental theorem of calculus for line integrals. So what the fundamental theorem of calculus does for us in one variable is it gives us a quick way of evaluating an integral when I know the relationship between a function and its antiderivative. So the Calc 2 FTC says that if you had a function g prime, so if you have some, if you take the integral from a to b of the derivative of a function dt, that you could undo that. So take the antiderivative of g and then plug in the endpoints of the interval and subtract, right? So the fundamental theorem of calculus is a tool for evaluating definite integrals by way of antiderivatives. So I would like to have something like this that works in the context of vector fields and line integrals if I can. So the main idea here is that if I wrote down something like, so let's assume for a second that we're working in the vector field context instead. And in particular, let's assume that I have a vector field f that is the gradient of some potential function little f. And if we're given some path r of t, we're going to define a function g of t to be equal to, let's see, f of r of t. Right, so what we're saying here is, now this function g, this is a function that takes a scalar input and produces a scalar output. R of t spits out an x, y, z. Little f is a potential function which turns it back into a number. So g is just a calculus 1 function. It eats a real number and it spits out a real number. So what that would mean is, if g is differentiable, if g is differentiable, then we would know that the integral from a to b of g prime dt would be equal to g of b minus g of a. This is a calculus 1 function. The calculus 1 fundamental theorem of calculus applies to it. But in the symbols that we've written down here, if I let g be equal to little f of r of t, I can actually write down what g prime is. G prime is equal to d by dt of g, which is d by dt of f of r of t. And the chain rule says that's equal to the gradient of f at r of t dotted with r prime of t. So the chain rule applied to this scalar field gives you that that is g prime. On the other hand, g of b is equal to f of r of b, and g of a is f of r of a. And so the fundamental theorem of calculus from calculus 1 gives us a version of the fundamental theorem of calculus that works for gradient fields. If you trace through substituting out g prime and g in this expression that we just wrote down, what you get is that the integral from a to b of the gradient of f at r of t dotted with r prime of t dt is equal to f of r of b minus f of r of a. That's a fundamental theorem of calculus. That says that if I have the integral of a gradient field dot ds over any curve c, that I could calculate this just by taking f and plugging in the finishing point r of b and subtracting f from the beginning point r of a. You can do the integral of a gradient field without parameterizing anything. The r of t doesn't even matter. This is just f of the end point minus f of the beginning point. This is a pretty amazingly useful idea that we can do this. I'm going to show you sort of in application what this looks like. So on this side, I have to put it here. All right, so let's look at something like, let's look at f is equal to x squared y. And the gradient of f is equal to 2x y comma x squared. And let's let our curve C be equal to something like maybe the quarter circle that starts at the point 1, 0 and wraps around to the point 0, 1. One way to produce that curve would be with the path r of t is equal to cosine t sine t, where t goes from 0 to pi over 2. So I could ask you, calculate the integral over that curve of the gradient of f dot ds. And the way we did this previously would have been pretty computational. The previous approach to this question would say, okay, well, by the definition of line integrals, the integral of the gradient of f dot ds over the curve C is going to be equal to the integral, okay, so the gradient of f is equal to 2xy x squared dotted with r prime of t dt. That's the definition of calculating the line integral of a vector field. And then if I plug in all of the component functions here, 2xy, well, so x was equal to cosine and y is equal to sine, so you're going to get 2 cosine of t, sine of t, and then x squared is cosine squared of t, and you're going to dot that with r prime of t, which is minus the sine of t cosine of t dt, and then you better evaluate that from 0 to pi over 2. This is what we did in 16.2. I evaluate a line integral by parameterizing the curve, plugging all the parts in, and then calculating. This is not going to be all that awesome a calculation, I guess, because you end up with the integral from 0 to pi over 2 of 2 times, so it's negative 2 cosine of t sine squared of t plus cosine cubed of t dt. And if you really love trig integrals, you can keep going here and evaluate this. There's not an obvious thing that makes everything cancel away. So, you could continue. Or, because we know that we're working with a gradient field, instead I could write down the integral of the gradient of f dot ds over the curve C is equal to the potential function evaluated at the end point, which was 0, 1, minus the potential function evaluated at the beginning point, which is 1, 0. Well, f is just x squared y, so you get 0 squared times 1 minus 1 squared times 0, which is 0. And I don't know about you, but I think this is significantly more efficient than doing it the other way. So we have the general approach to any parameter, calculating the line integral of any vector field. But in the special case of gradient fields, I don't need to do that. I can just evaluate the potential function at the beginning and the end of the path. To give you another example, where the answer isn't 0, and one that we could trace all the way through, if I wrote down, say, the same function and the same gradient, but now instead of the curve being the arc along the circle from 1, 0 to 0, 1, I let the curve C be equal to a straight line path that begins at the point 1, 1 and ends at the point 2, 2. Then r of t in this case would be equal to tt, where t goes between 2 and 1. R prime of t is the vector 1, 1. The integral over the curve of the gradient of f dotted with ds would be equal to the integral from 1 to 2 of 2xy x squared dotted with the vector 1, 1 dt, if we are doing it the parameterization way. which would get you the integral from 1 to 2. Well, I better plug in the x and y values. So x was equal to t and y is equal to t. So you get 2t squared and t squared dotted with 1 dt, which is equal to the integral from 1 to 2 of 3t squared dt, which is t cubed evaluated from 1 to 2, which is 8 minus 1, which is 7. So if I parameterize the curve and run it using our definition of the line integral of a vector field, I get 7. But because I'm integrating a gradient field, I can use the fundamental theorem of calculus. And the fundamental theorem of calculus version of this would say, oh, well, why did you do all that? Instead, what I should have done is I should have taken f of 2, 2 and subtracted f of 1, 1 from it. Evaluate the antiderivative of the gradient, which is the potential function, at the end point minus the beginning point. 2 squared times 2 minus 1 squared times 1 is 8 minus 1, which is 7. The fundamental theorem of calculus allows us to get away with not parameterizing the curve. Yep.
You can have any path that goes between 1, 1, and 2.
Yes.
Like you go like
So,
I'm not being 7.
and that's I'm going to hook this up to the next definition. No matter any path that you choose between 1 and 1 and 2, 2, you will get 7 as the answer. Because the only thing that mattered was the beginning and the end point. And that should remind you of ideas from physics called conservative forces, right? Conservative forces are forces where the only thing that matters is your displacement from your initial position to your final. It doesn't matter how you did it, it just matters where you started and where you ended. Work in a gravitational field, for example. It does not matter what pathway I took. If I start here and then I walk to the top of Baker, I could walk all around campus first, and from the perspective of potential energy put into the system by working against the gravitational field, it doesn't matter how I did it, it just matters how high I went. Right? The path didn't matter. That is essentially what is at play here with gradient fields. So, in fact, we can go one step further and say a vector field that has this property is called conservative. If a vector field f is equal to the gradient of some potential function for some potential f, then we say f is a conservative vector field. Conservative vector fields typically arise in the study of electromagnetism and gravity, for example. So if I do have a conservative vector field, then the fundamental theorem of calculus applies. So it would be great if I could always do this. In practice, what happens is, in many cases, you might be given a vector field and you don't actually know if it's a conservative vector field or not. So somebody could show up and write something like, hey, I got a vector field for you. How about, here's a vector field. F is equal to 2xy plus y times the cosine of xy, comma, x squared plus x times the cosine of xy. And I would really like to integrate that vector field. And I don't want to parameterize things because look at that. Ugh, it's going to be terrible, right? Cosines with t's running around inside. If that was conservative, I could just, okay, so here's what your chain of logic should be. If it was the case that the gradient of that capital F here, our gradient field, was equal to the gradient of little f, if there was a potential function, then, and I knew what it was, then I could write down the integral over c of f dot ds is equal to f of the end minus f of the beginning. So there's two questions here that we need to think about. Question one is it the case that there is a potential function? If I just give you a vector field, can you pick off that it's a gradient of some potential? And two, how do I find it? Because if I could do that, if I could identify when I know there's a potential function, and then once I know there's one, find out what it is, then I could know that I could use the fundamental theorem of calculus. was pointed out to me in the last class that I have not introduced the idea of curl yet, so we will talk about curl in 16.4. I think I mentioned it briefly in passing, so I won't refer to that. I'm going to tell you what the condition is first, and then we'll try to figure out what it means. So the first version of this condition is as follows. If you have a vector field F, and in many fields, P and Q are the letters that are used for the first and second component of the vector field. So you can think here, P is a function of x and y, and Q is a function of x and y. And the derivative of Q with respect to y minus the derivative of P with respect to x is equal to 0. Then f is the gradient of some little f for some potential f. So what on earth is that checking? Because that seems kind of random.
It looks like it's checking that both that P's antiderivative and Q's antiderivative should be equal.
So it is, but this is a condition on derivatives, not antiderivatives, right? So I'm going to write down a diagram that's going to explain where this condition. Oh, go ahead.
It's like Fubini, right?
Almost. There's another version. So Fubini is like a integral switching theorem. I think you're thinking of a theorem. It's a different name for what you're thinking of. That's called Clairaut's theorem. This is exactly checking Clairaut's theorem. So this bit right here is essentially a check that Clairaut's theorem is true. So remember, Clairaut's theorem said that f of xy was equal to f of yx for a sufficiently nice function f. So I'm going to draw a picture of what this condition means. And it will also indicate a method of finding the potential function. If I had a function f, and I calculated d by dx of it, and I landed on p would be equal to the derivative of f with respect to x, right? And if I calculated the derivative of f with respect to y, if there was a potential function, and I got fy, that should be the function q. If I then took the derivative of p with respect to y, that would get me dp, dy, but that would also be equal to fxy, the mixed partial derivative of fx with respect to y. And if I took the d by dx derivative of fy, that should get me f of xy, which is equal to dq dx. If there was a potential function f that was twice continuously differentiable, so the Clairaut's theorem held, what that would say is it shouldn't matter how I reach this condition at the bottom. fxy and yx should be equal to each other. That's Clairaut's theorem right there. And if I labeled fx as p and fy as q, this condition is just checking to see, are these actually the same? Okay. There's a whole other physical interpretation of this that I'll talk about when we talk to curl. So I'll give you the preview, which is this also represents the fact that the vector field has no local rotation. So this is called an irrotational vector field as well. If you've seen that, and you guys are pretty early in your careers, but if you've seen that in a fluids class or like a dynamics class, this means a rotation-free or irrotational, curl-free vector field. Yep.
So shouldn't it be dq dx and dp dy?
Did I do it backwards? Every single goddamn time. That's on video. Yeah. I did that in an earlier class and told myself I wasn't going to do it, so I reversed myself when I wrote it down and I still got it wrong. Yeah. Yeah, dq, dx, dp, dy. So let's write something down and we'll see. So if I wrote down that function f, which was 2xy plus y times the cosine of xy and x squared plus x times the cosine of xy. Question one is that a vector field that has a potential function? And the approach is to identify all the pieces. This bit right here is the function p. This bit right here is the function q. If I calculate, that's pretty dim. If I calculate dp dy, I'm going to get, okay, so the derivative of this with respect to y is going to be 2x plus cosine of xy plus y times minus the sine of xy times x by the chain rule or product rule. And likewise, dq dx, so if I take the derivative with respect to x, I get 2x plus the cosine of xy plus x times, okay, the derivative of this with respect to x is going to be minus the sine of xy times y. And if you look at those for a second, they're equal to each other. dq dx minus dq dy minus dp dx is dq dx minus dp dy is equal to 0. Sweet, okay, so now we're all excited because that means, look, we did it. We checked the thing. This is an annoying part of math called an existence theorem. It says there exists some function f that has this as its gradient. So there is some potential function f so that the gradient of f is equal to our vector field. I didn't tell you how to find it. I just told you there is one. The problem with wanting to use the fundamental theorem of calculus is I actually need to know what this f is. So I've indicated, I think I did an example of this earlier. The method that we're going to use to recover the potential function is called partial integration. So I'm going to imagine, now that I know that there's an f, if I took d by dx of f, I get the function p. Whatever the f happens to be, when I take d by dx, p is the thing that comes out, which is equal to 2xy plus y times the cosine of xy. And on the other hand, if I took d by dy of f, I should get q, which is equal to x squared plus x times the cosine of xy. Because remember, the gradient of f, which is the gradient is equal to fx, fy, is also equal to pq. Okay, well, if I found p and q by taking derivatives of f, how should I find little f? Should probably take integrals, right? So if I took this and I integrated it, integrate with respect to x, I should recover little f. So what is the integral of this with respect to x? So we calculate the integral of p dx, and f should pop out because I'm undoing the derivative. Of course, it's a partial derivative. So what do I get? X squared y plus, okay, sine of xy plus, yeah, so I would say c of y. Why c of y? What is that doing there?
Because if you take the derivative with respect to x, any y goes away.
Okay, so it's like the arbitrary constant that shows up when you're doing integrals for the first time with indefinite integrals. But partial derivatives don't just kill constants. They kill anything that's purely a function of y. d by dx of c of y will be 0. So partially integrating means that I've potentially not seen a whole function of y that I've missed. Now what I should do is I really like to know what that c of y is. What could I do? So yeah, why don't we just keep going? Let's chase this down here. If I took if that is f, this is df dy. So let's actually calculate df dy. df dy is equal to x squared plus the cosine of xy, and then by the chain rule we get out an x, plus c prime of y. I don't know what c of y was, but I know when I took its derivative, I got c prime of y. And now I compare. These should be equal to each other. This is df dy. This is also df dy. So they're the same function. So you set up the inequality and say, okay, well, this cancels with this, and this cancels with this, and that means that c prime of y, it's kind of a boring example, is equal to 0, which means that c of y, now you can integrate 0 to get the answer, it's just some constant k. And so the answer to the question is this. You replaced c of y with now what you know it to be, and now you can just check your answer. df dx is equal to 2xy plus the cosine of xy times y. df dy is equal to x squared plus the cosine of xy times x, which is this. What the constant is doing there, if you're curious, is the potential function has two different features. Remember that derivatives only see it like up and down, right? They see slopes, but they don't tell you like how tall you are. X squared and x squared plus 10 has the same derivative. So you can think about this as sort of locating an initial point. If I tell you how high the surface is, then the derivative will be unique after I've told you where you're located, what your absolute starting point is. I guess the point here is this is picking up the idea that this function and this function have the same derivative. They have different initial points, but the derivative is the same. Two different potential functions could have the same gradient structure, but be located at sort of different initial heights. All right, let's look at another, a more interesting example here. All right. So now let's look at the function, the vector field f is equal to 2x plus y, comma, x plus 2y plus 1. A typical sort of exam question will say, is that vector field conservative? And if it is, find its potential function. Is f conservative? That is to say, is f the gradient of some potential function? Is f equal to grad potential? P is equal to 2x plus y. Q is equal to x plus 2y plus 1. dp dy is 1. dq dx is 1. Oh, they're equal. It's almost like I'm thinking of potential functions and taking their gradients to make sure that these actually have answers. That means that dq dx minus dp dy is equal to 0. So yes, there is a potential function. Now let's find it. Okay. So what I'm going to do is write down the diagram. You don't technically have to do this, but I will say that people seem to have a lot more success when they're organized about their approach to these questions. So 2x plus y sits here. X plus 2y plus 1 sits here. We can go the other direction this time. Let's actually go this way. Let's start with this, and we'll integrate. Okay, well, this was a derivative with respect to y, so let's take the y integral. A lot of times people will just pick the thing that looks easier to integrate for which branch they want to work on. So if I integrate that with respect to y as a partial integral, integral of q dy gets us f is equal to xy plus y squared plus possibly some function of x that I missed. If I keep going, because I'd really like to identify what this piece is missing here, and the question I got asked last time is, why do we even need that? If you stopped here and you took the derivative of this function with respect to x, and that wasn't there, you would just get y. So there's this extra piece that function by itself can't produce, right? This derivative does not have a 2x as part of its derivative. So what I'm looking for is, the bit that I missed that actually creates the 2x when I take the x derivative. That's kind of the goal, is to figure out what needed to be here so that that part of the derivative is actually there. And of course, if you think about it that way, you could just eyeball that it must be x squared. Yep.
Are you integrating the 1?
Oh shit. Yeah, let's chuck the 1 in too. That'd be nice. Yeah, we said. Yes, I totally was. Yeah, xy plus y squared plus y. So if I took this derivative with respect to x, I get out y plus, okay, well that derivative is 0, and that derivative is 0, and the derivative of c of x with respect to x is c prime of x. But these are both supposed to be the same thing. This was the p that we were given, and this is df dx, and those are equal to each other. So we must have that y plus c prime of x is equal to 2x plus y. We cancel anything that we have in common. So c prime of x is 2x, which means that c of x is equal to x squared plus some unknown constant c. And that means we can go back and fill this in so that our potential function f was xy plus y squared plus y plus x squared plus some arbitrary constant c. And then you can just check to make sure that the derivatives match. The derivative of this with respect to x is 2x plus y. The derivative of this with respect to y is x plus 2y plus 1. Now, if I was writing an exam and I was really trying to drive home the fact that I wanted you to not parameterize a curve and use the fundamental theorem of line integrals, the way this question would have been written was, question 1, is f conservative? Question 2, find the potential f. So you've done that. Question 3, compute the integral of f dot dr, so the line integral of f, over the curve c, where c is the curve. Okay, so we'll start at minus 1, 1. And then we'll go like this. Oh, and then I'll put 2, 2 right here. And then I will do. How do I make sure that you don't blow this question? If you try to parameterize that, you're nuts, right? So I try very hard to write questions that I make sure that people don't blow by trying to do it the hard way when I've given you the easy way, right? So the point, I probably won't be this ridiculous, but the point is, when you're working with conservative vector fields, this is the magic of conservative vector fields, of gradient fields, is that all that matters is this point and that one. All that matters is the beginning and end point. So you've identified the vector field as conservative, you found the potential function, and that means that you know that this is equal to f of 2, 2 minus f of minus 1, 1. You can just evaluate the values and plug them in. Yep.
Do we need to find if f is conservative, or will just doing the partial integral find that out?
I mean, you in many cases you don't want to bake the, okay, so from the standpoint of math homework, if I ask you if a vector field is conservative and then find the potential function if it is, and it's an exam question, you pretty much know going in that it is conservative and you're just checking to see that it is. So probably if I was being honest, the question wouldn't be is f conservative, it would be verify that f is conservative and then calculate the potential function. So yeah, generally like when you're working with these things in the context of a math book, if I ask you to find a potential function, then you know the vector field is conservative, right? There's another question here, though, which is, what if I gave you a vector field that wasn't conservative? Like, what could you do? Actually, I didn't get a chance to ask this in the last class, so this is sort of like our freely creative part of the class here. So I give you an f, a really easy one, right? Like some kind of vector field f, which is built out of pieces pq, and then you calculate dq dx, and you subtract dp dy from it, and you don't get 0. So imagine for a second that this represents some kind of vector field where, if you think about vector fields as either force lines or force vectors, or you think about it as velocities of fluids, right? There's something wrong with the way this vector field is set up, in the sense that that condition doesn't hold. I can't use the fundamental theorem. There's no potential function. Just hit me with your craziest ideas for what you could do to fix it. Make it conservative. How?
Adding thermal energy to one side.
Adding thermal. Oh, okay. All right. So no. This is so. Yeah, you really want to fix this. You want to somehow repair the vector field so that this would be true, because then you could use the fundamental theorem of calculus on it, right? You would get a potential function for a different vector field, but one where you knew what the modification was. And so the answer is this is that's exactly the way that you do it in differential equations. If you've ever seen them in any context before, this is part of a topic that is called exact equations. And the tool is you just multiply your vector field by another function and fixes it. There's a formula for, now I want you to think physically what that would mean. I have some vector field describing the flow of fluids, and it's not conservative. So I can't use the fundamental theorem of calculus, and there's no potential function. So what I do is I go through the vector field and I adjust the velocities. Like, hey, I got this function. I adjust all the velocities to take all the rotation out, and then magically it turns into a thing that does have a potential function, and I can solve the equation. It almost feels like cheating. But that's kind of like, if you're going to take 244 or 242 if you're a math major, this is one of the core techniques, actually. And when they teach 242, because it does not have a prerequisite that requires that you know anything about vector fields, they won't actually... I will do this where I connect this up with 241, but if you take 242 and you're leaving me, you're going to learn exact equations and probably with no reference to vector fields. But that's essentially what's going on, is that there's a way to fix vector fields so that they do have potential functions. All right, so the next thing that we're going to do in the class, I don't have time to talk about today, but I'll give you a little preview, is the most important theorem probably in 241 and the basis of a ton of other mathematics. This incredibly powerful theorem called Green's theorem. And what Green's theorem gives you is a way to... Where did all my nice chalk go? I'm lost. Whatever. I'll do it with blue. Or yellow. So 16.4, I encourage you to read ahead. This is a chapter about a theorem called Green's theorem. And what Green's theorem is going to give us a way is to relate the integral on the inside of a region. So there's going to be some region D here. It's going to give us a way to relate a double integral on the inside of a region, the double integral on the inside of a region D of the scalar valued function. In fact, one way of writing it is dq dx minus dp dy dA, a certain kind of double integral on the inside of a region to an integral on the boundary of the region. And the thing that we'll put here will be p dx plus q dy. So what I'm thinking is, this is kind of a pretty striking idea. Just ignore like the symbols for a second. And the idea is, I have a double integral of a scalar function on the interior. If you like physics, this is basically picking up the tendency of the field of a vector field to rotate in the interior. And I can turn it into an integral contained entirely on the boundary. So C is the curve that travels around the outside. So this is a relationship between something about the conservative, like failure of a vector field to be conservative, and what's called a circulation integral. So the integral, a double integral that is an area integral on the interior of a region is going to turn out to be a single integral of a vector field on the outside. So we'll talk about exactly what that means. I will say that one of its funniest applications, and I encourage you to look this up, I will bring a video if I can find a good one. There's a tool called a planimeter. And what it's used for is it's this mechanical tool where if I had this on a piece of paper in front of me, and I was an engineer in the 1960s or 70s, and I really wanted to know the area of that region, because I was doing some sort of physical calculation where it didn't matter that I knew that, I could take this pen that's hooked up on an arm to this machine, and I could just draw the outside curve, and a little number would, like a spinning dial, would tell me the area of the interior. It's like the most bizarre, awesome mechanical like tool that I know of in this kind of mathematics, right? It's a mechanical integrator. Not a computer, it's just gears. All it does is you draw this curve, and the little spinning dial tells you the area of what it was that you drew. So I will bring a video of this. We will explain how it works, and Green's theorem is going to be the thing that does it. So Green's theorem is also the foundation of complex analysis. Have you seen that before? Yep. Well, if you don't close the curve, then it's basically telling you the area of a curve that like would have that like total thing that you drew. I don't know what the interpretation is in that case. All right. I'll see you guys next time.